Hello students, in this video we'll prove Kronecker's theorem. Kronecker's theorem states the following. It said that if gamma is an irrational number, then the sequence of fractional parts of gamma, gamma of n, the sequence is equidistributed on 0, 1. Okay, so let's come up with the terminology and let's try to understand this theorem. Okay, so a couple things we need to, a couple bits of information to sort of unpack this, right? So first, notes. The first thing is to note for that x in R, we said that floor of x is the integer part of x. Okay. And if I look at x minus the integer part of x, then x minus the integer part of x, that's the fractional part of x. So this is called the fractional part of x. Fractional part of x. And of course, the fractional part of x is just what we get on the end of the decimal expansion, right? So if you have like 3 point something, it'd be the whole point something, right? Okay, excellent. So for example, if we said what's the fractional part of 3.14, it would just be 0.14. So the fractional part's always a number that's between 0 and 1, inclusive of 0, exclusive of 1, okay? All right, excellent. And now, good, what do we mean by equidistribution, right? So that's what fractional part means. So a sequence, so definition, a sequence, A1, etc., AN, is equidistributed on 0, 1, if for any subinterval, AB, a subset of 0, 1, we have the limit as n tends to infinity of the cardinality of the set of indices 1 through j, such that aj is in the interval a to b. The cardinality of that set over n, the limit as n goes to infinity tends to b minus a the length. So in other words, it basically sort of is well distributed on the entire interval 0 to 1. Okay, excellent. Now I want to show this is so. So what we're going to do is the following. So the idea behind this is really simple. We're going to use Weyl's theorem, right? And so we're called Weyl's theorem. Stated that if gamma was irrational, then what? Then we have the integral, we have the sum, 1 over n, j goes from 1 to n, of what? Of f of 2 pi j gamma converges to 1 over 2 pi, the integral from negative pi to pi, of what? Of f of x dx. Okay? And so the corresponding result is I can rescale this, right? And I can conclude the following. I can conclude that the same thing is true on an interval of length 1. So I can conclude the sum, j goes from 1, by the same argument, j goes from 1 to n, f of j gamma is going to converge to, just the integral from 0 to 1 of f of x dx. Okay, by just rescaling 0 to negative pi to pi to be 0 to 1 by changing coordinates, right? If this is true if gamma is irrational, and this is as n goes to infinity, Okay, excellent. And so now the key is that we're going to use this version of Weyl's theorem. So what we're going to do is we're going to say that, note that this cardinality over here, so the cardinality of the set of points, j between 1 and n, such that this sequence over here, gamma n, such that the fractional part of gamma j in this case is in the interval AB over n is simply just equal to 1 over n, the sum, j goes from 1 to n, of the characteristic function of the set AB of gamma times j. Gamma times j, where I extend this characteristic function. This is just the typical characteristic function here. So I'm going to put, maybe I put a sub p over here, okay? And so, of course, we know what the typical characteristic function is, right? The typical characteristic function says here's a, here's b. There's 1, for example. And what that is, it's just going to be 0 to 1. Between a and b, you're going to get a 1. And then you're going to get a 0 everywhere else. Okay? Like that. And then we make it periodic, right? So that we periodically extend it. So if I go from 1 to 2, right, I would just have a plus 1, b plus 1. Just shift everything by 1. I'd have the same thing over here. So we're making a periodic extension of this characteristic function, like so. Okay? Now, what's the downside of this? The downside of this is that this Weyl's theorem is true for what? This is true for f continuous. F continuous, and this function is not continuous, but we're going to get around that by an approximation argument. So what I claim now is I claim that by Weyl's theorem, this is going to converge to, by Weyl's theorem, just what? The integral from 0 to 1, the characteristic function of a b of x dx, which is just b minus a, because it's just the integral from a to b, right? And so now, of course, the question becomes is how can I use Weyl's theorem if this function is not continuous? Well, what we're going to do is do an approximation scheme. I just need to show there are 2 continuous functions that are arbitrarily close to this that can approximate this characteristic function. So here's what we're going to do. So let's look at this approximation scheme. So here's 1, here's 0, and here's my characteristic function a and b. So the characteristic function looks like this, just 1 over here. Okay. And so now what we're going to do is if we let epsilon be greater than 0, we're going to go over here to a minus epsilon, a plus epsilon, b plus epsilon, b, that's a b minus epsilon actually, b minus epsilon over here, b minus epsilon, b minus epsilon, and then b plus epsilon over there. And what we're going to do is we're going to fit in 2 continuous functions that approximate this characteristic function. The first one we're going to do is going to be bigger than this, so let's look at this function over here, which linearly slopes up, and then linearly slopes down over here. That's our first function over here. That function over there is I'm going to call that u epsilon. Okay? For that's a height of 1. All right, and then I'm going to make a function over here that's the same thing. That goes up. That's 0. 0, 0, 0, 0, 0, 0, 0. Then it goes up to a plus epsilon, go up linearly, approximate, and then come down over here. Now, it doesn't look like it from this picture, but epsilon is extremely small, right? So this large trapezoid and this small trapezoid are majorize and minorize this function over here. So in other words, our characteristic function, so L epsilon, is less than or equal to this chi AB u epsilon. And the area that's missing over here is just what? So the area of this little triangle over here is exactly what? So I have a length of epsilon and a height of 1, so that's an epsilon over 2 and epsilon over 2. So there's epsilon over there. The areas differ by epsilon. And I know that as epsilon goes to 0, these functions L epsilon and u epsilon will basically tend to this characteristic function. So these L epsilon converges to chi AB as epsilon goes to 0. And u epsilon converges to chi AB as epsilon goes to 0. And so since the Weyl theorem is true for these functions L epsilon and u epsilon, and that the result that you'll get will be a plus minus up to a factor of 2 epsilon over here, plus minus 2 epsilon, as epsilon goes to 0, we see that this result is true. So therefore we have this equidistribution of these of this set over here of gamma n as n goes from 1 to infinity. So if gamma is irrational, I have an equidistribution theorem for the fractional parts of the multiples of gamma. Thank you very much.